Hey everyone, back for another video today in our continuing series on differentiation, and this one's on how we use differentiation. It's for AS Maths, the C1 module uh, of the A-level Maths course. Okay, our objectives. Find the equations of tangents and normals to the curve, and also find regions of increasing or decreasing rates of change. So, quite a lot in today. But in the second series of lessons, after the last time we looked at how to differentiate by rule and the different types of differentiation and what differentiation means. If you haven't seen that video, you should go back and check the one on differentiation that comes before it in this series. Okay, in the last lesson, just like I said, we looked at how we differentiate and the general idea of differentiating an expression and what that means, etc. In this one, we're going to take that on a little bit. We looked at a little at how we do this already, but we're going to find the equation of a tangent to a curve. What you should know, well, do you even know what a tangent is at this stage? I'll bring it back to circle because it's probably the place where you may have seen the word tangent beforehand if you hadn't discovered it. A tangent is a line that touches the outside of a circle at only one point. So if I show you a circle, like so, and I put a line up against it there, and that line will touch at only one point, roughly around there, like that. Alright, and that's a tangent. So the line only generally touches or rests against the thing at one point. If you want to think of even of a ball on a table, if you set a ball on a table, it only makes one tiny point of contact with the entire table, even though the rest of the ball seems like it's being in contact. It only makes contact at one specific point. So it can also be a line that touches a curve at a single point, and generally in calculus and stuff, we're talking about curves. So this portion of the line could be the part of a curve. And let's see a couple of examples as we go through. The tangent gives you a snapshot of that moment in time. So that generally means is that the rate of change can be measured at any given point along the line, or gives us a way to measure how quickly things are changing, whether they're getting bigger or smaller at any given points of change. And like many aspects of A-level maths, you understand the theory of what we're going to do, and then we'll move on to practical examples in the real world, and I'll try and combine a little bit of both in this short lesson. So, remember when you're trying to get an equation, you're trying to get it in the form y equals mx plus c, or in A-level, a lot of times it's going to be ax plus by plus c equals naught, where you're getting your x and your y terms all to the left, along with your constant term. The y equals mx plus c is a bit more of the GCSE form, but in many cases, it's still very valid for A-level. So our objective, we're going to find the equation of a tangent to a curve. And the example we're going to find the equation of a tangent to a curve by finding the gradient when we differentiate. So from the last lesson, we found that when we differentiate, we get the gradient function, or it gives an expression for finding the rate of change at any point. The rate of change in a line is the gradient. So you should already be familiar with this if you've mastered the last lesson. Like if I say, if you haven't, go back to the last lesson and have a look. But we're going to do it for the line of the curve y equals 3x squared minus x plus 1 at the point where x equals 1. So when we differentiate this, it'll be 2 times the 3 gives us 6, and then 2 minus 1 gives us 1, so it'll be 6x, and then minus 1x differentiated just gives us minus 1. So our gradient function, or our differentiated function, is 6x minus 1. To find the gradient at this point, we substitute the x equal to 1 from the question into your gradient expression. So that'll be 6 times 1 minus 1, which will give you 5. This gives us the value for the gradient m to be 5. And if we use the equation y minus y1 equals m upon x minus x1, which is the equation that we generally use for when we've got the gradient and 1 point on the line, we'll be able to find the equation of the line. However, you can see that we also need the y coordinate. We're missing the y coordinate. We've got x equal to 1. I'm going to need the y coordinate. Do you remember your lullaby from the last lesson? Well, what I told you to rhyme before you go to sleep every night was that the original curve, y equals 3x squared minus x plus 1, describes the relationship between y and x. The differentiated expression does not. It only gives us an expression for the rate of change. So if we want to find out what x is in terms of y, we'll have to go to the original function. And the differentiated expression doesn't count. So when we substitute x equal to 1 in, which is our value at this point we want to find out what y is worth, we put y equals 3 times 1 squared minus 1 plus 1, and that gives us 3. So therefore we can say that the tangent touches the curve at the point 1, 3. Using y minus y1 equals m upon x minus x1, we can get the equation of the tangent at that point to be y minus 3, which is your y coordinate, equals 5 upon x minus 1. We'll multiply out our bracket and get y minus 3 equals 5x minus 5, and bring in our minus 3 over. We eventually get that y equals 5x minus 2, and that's the equation of the tangent at a point in the circle. So when I give you, like for instance, an x coordinate, so there are a couple of stages. We differentiate it, that gives us the gradient at any point along the curve. We knew what point we wanted to put in, we substituted that in. 1. We had to find out a y coordinate. In some cases they'll give you the y coordinate already, but I thought I would do that version because it shows you the extra step. And then we use our y minus y1 equals m upon x minus x1. If you're used to doing ordinary two-stage geometry on the left, or from before, you will have found out the gradient and then used the y minus y1 equals m upon x minus x1 just like before. So it is just like coordinate geometry and straight line geometry that you've seen before, except that you differentiate instead of using the y2 minus y1 or the change in y over the change in x. And that's finding the equation of a tangent to a curve. Second part comes to the idea of what is a normal. I've asked you to find the normal to a point, and you may have covered this again in other parts of the course, maybe covered it in coordinate geometry, but I'm going to bring you back by looking at the tangent of the circle. There's a circle, there's a tangent. A normal is another name for the line that is perpendicular, which means at 90 degrees, makes the corner of a table, some people might say, to the tangent at a point where it touches the circle. So our point where it touched the circle was there, and so a line at 90 degrees to that would look like something like that. Okay, and that would be the normal at that point. How can we work this out? Well, you may remember from before, the perpendicular gradients multiply together to give you minus 1. We can work out the gradient of our tangent, just like we did in the last example, and then find out what multiplies that to give you minus 1. Use some simple algebra to help you do that. For example, if the gradient of the tangent is 2, we can work out the gradient of the normal m by doing 2, which is the gradient of the tangent, times the gradient of the normal m equals minus 1. And if I rearrange that, that'll give me m equals minus a half. QED, as it's quite nice to say. And you'll see me doing this quite a bit as we'll do in the next couple of examples. Okay, you ready? Most of the problem is identical to the previous one, aside from that bit where you change the gradient. So we're going to find the equation of a normal to a curve in the example where we're given the curve y equals 3x cubed minus 8x squared at the point where x equals 2. Used a curve that's not a quadratic to show you that the curves aren't always going to be quadratic. So in this one we have a cubic nature. And we start off as before by finding the gradient of the curve at any given point by differentiating. If I differentiate, the 3 times the 3 gives me the 9, the 3 minus 1 gives me the 2, so 3x cubed differentiated gives me 9x squared, and minus 8x squared gives me minus 16x. To find the gradient at this point, we substitute x equal to 2 into our gradient expression, and dy by dx is equal to 9 times 2 squared minus 16 times 2, which is 36 minus 32, which is 4. This gives us a value for the gradient of the tangent to be 4. Now we must find the value of the normal, or the value of the gradient of the normal. So we do our gradient of our tangent, 4, times the gradient of our unknown normal, which I'm just going to call m, and those multiply together to give you minus 1. I rearrange the 4's multiplying by the m. Want to do the inverse operation of that, that'll give me m equals minus a quarter. And that's the gradient of the normal at that point. Except we don't know what that point was again. I mean, we had the x value, but we don't know what the y one was. Okay, so we'll substitute our value of x into 3x cubed minus 8x squared, remembering that that is the one that gives the relationship between y and x, and not the differential expression. And that gives us 3 times 2 cubed minus 8 times 2 squared. That gives me 24 minus 32, which is minus 8. Therefore, we can say that the normal touches the curve at the point 2 minus 8. Using our y minus y1 equals m upon x minus x1, just like before, we get the equation of the normal at that point to be y minus minus 8 equals minus a quarter x minus 2. That gives me y plus 8 equals minus a quarter x plus a half. Usually at A level we multiply across by the Hash common denominator, if you know what I mean, or the Hash value of the denominator, which is 4. If I do that, I'll get 4y plus 32, which is 8 fours, minus a quarter times 4 gives me minus 1x, and a half times 4 gives me 2. I'm going to bring that all over to the left, so we get 4y plus x plus 30 equals 0, and that's the value of our normal at the curve at that point. Okay, so very similar to the last example that we had where we defined the equation of the tangent. In this one, we're finding the equation normal with that one extra step where we multiply the two gradients together to give us minus 1, and then we do it just as before. If you'd got something like that and brought the plus 8 over and made it minus, it would have been just right. You'll generally see the form of the answer, but ax plus by plus c equals 0. They'll usually tell you in the question what way to leave that. And that's our final equation of a normal to a curve. So what does that all look like? I thought I would show you what this looks like as far as the graph goes. So if I show you what the original curve looks like, it looks like this. That's our 3x cubed minus 2x squared, or 4x squared. And that's it. So a cubic graph will have two changes of direction in it, you know, 1 and then 2. If I add in the gradient function, or the graph of what the gradient function looks like in blue, you'll see that that is what it looks like. Now, you'll know that when you differentiate a expression, it gets becomes a power less than it was beforehand. So a cubic one with two changes of direction will become a graph with one change of direction, or your normal quadratic graph, your U or your N shape. And when I put the normal in, you'll see it here. I've marked where the point where the tangent would have touched 2 minus 8, and the normal would be at 90 degrees to that, and that's our normal at that point. Now, I've done those in Desmos, and Desmos.com. If you want, you can plop in an awful lot of the values, but if you scan that QR code there, it'll take you to the setup of that particular graph, and you can have a play about. You can do the same thing for x equal to 1, for instance, and find out if you get the right value for y, and whether you get the equation of the normal correct, etc. as well. You can put that into that function and then have a play with that if you like. But I think it's a generally good idea to try and graph these things if you can by hand, or even very roughly. You'll probably not want to graph the gradient function, but certainly the original curve you can have a stab at, and using some of the ideas of how to sketch curves, and do the same with your normal function, just to see whether it makes some sort of sense. Okay, we're going to move on to rates of change. And like I've said before, differentiating gives you a general expression for measuring the rate of change at a given point. So, if I show you a surface, and I'm going to pour water out onto it. So it's very difficult to pour it out at a completely constant rate, so at a steady rate. It's more likely it's going to come out at a variable rate, so there's going to be a bit comes out, and then it's going to slow down, then it's going to speed up, something like that. If I could graph the rate to give us a function or expression, give us the function or expression model on it, we could find out how quickly we're pouring the water out at any given time by differentiating as before. So differentiating gives us the expression we can use to find this out. And that's the bit of theory behind it. So rates of change combine usually inequalities with calculus, although not always, but you'll see this coming along. And our second objective is find the rate of change of increasing and decreasing functions. So it can be helpful to know whether actions are on the increase or the decrease as you're going through. And I'll work through two examples of these questions, but in general your approach should be the same. First example I'm going to do one water is dripping into a bowl, similar to the example that I used. The function f of x equals t squared over 4 plus 3. This models a reaction where t represents the time and x is the radius of the water in millimeters, assuming that the water kind of makes a cylindrical, you know, it makes a circle when it hits the bowl. The bowl is circular, so therefore it's going to be filled in the circular bowl. I thought that was the best way to model this. So can you tell whether the function will increase, decrease, or change over time? And what is the rate of change after 5 seconds? So if we look at the first part first, we can tell that it's increasing, decreasing, or changing by looking at the graph of the derivative or the gradient function or the rate of change function. You can also use your common sense for this, as I'll come back to in a minute. But in general, you can tell what's happening at any given point. And if you can sketch the graph of the function, and by say sketch, I mean sketch. I mean you don't need a wholly accurate graph, but you can make a quick sketch of what the graph should look like. It should help you. So if I do the same, remember that differentiating gives an expression for the rate of change, and if I differentiate, I get function the derivative of x, f dash of x, equal to be t over 2, because 2 times t over 4 becomes a half t, and that's the graph of y equals t over 2, or x equals t over 2 in this case. Okay, you will see that the line's always increasing. It's going up to the right, and it increases at a steady rate. And this kind of makes sense, because the amount of water is going to keep increasing in the bowl. You know, if you've got water dripping into a bowl, it's going to continue increasing. So, with that in mind, we were asked to find the rate of change after 5 seconds. We found that the derivative of x, f dash of x, was t over 2. We just substitute in t equal to 5 and get the rate of change then to be 2.5. That happens to be millimeters per second. It means that at 5 seconds the rate of increase is 2.5 millimeters every second. Okay, and that's that question done. Fairly straightforward. But what I'm going to take you on to do a past paper, and this one is from January 2011, a C1 paper, the SAFE papers. And it says, the number of bacteria B in a petri dish after time t hours can be modelled by the equation B equals 4t plus 64 over root t plus 7, where t is greater than 0. And I'll tell you at the point where it becomes important later on. There'll always be a key point in the question. You find it a lot in mechanics questions when you come to study mechanics. But there's always be a point where this means something. And you may or may not be aware of it, but it'll be an assumption that you make later on. We are asked to find the number of bacteria after 16 hours for a mark. Find the rate of change of the number of bacteria after t hours for 3 marks. And hence find the range of values of t for which the number of bacteria is increasing. And that's also 3 marks. If I take part 1 first, this function isn't easy to graph, so even though we said you should try and sketch the function, you certainly can. You can stick numbers in like -5, -4, -3, -2, 1, 0, and kind of get a feel for what the graph looks like. But in some cases, it's not easy to do. And for a graph like this, because it's a combination of a 1 over square root t and a constant, you know, you might find it tricky to do, and you wouldn't reliably maybe use it to guide your answers like we did before. It might be too time consuming in the exam. So the original equation describes the relationship between the number of bacteria and time t. To find the number of bacteria after 16 hours, we substitute t equals 16 in the expression. Remember that this is the original expression that says how b relates to t. Our differentiated expression always just gives you the rate of change. Keep coming back to this again and again and again, because it's one of those things that people always get confused about. So when I put t equals 16, I'll get 4 times 16 plus 64 over root 16 plus 7. That gives me 64 plus 16 plus 7, and that gives me the number of bacteria to be 87. First part done. Only a mark, nothing too strenuous or bad about that. If I move on to part 2, the rate of change, like before, is found by differentiating. So if I take my original expression like that, what have I got to do so that I can differentiate it? Well, one of the rules that we looked at in the last video was that we need to convert it to indice form before finding the derivative. So if I change the 1 over root t to be t to the minus a half, and then differentiate, I'll get 4 times the t becomes 4. The minus a half times 64 gives me minus 32. Take 1 away from minus a half gives me minus 3 over 2, and plus 7 disappears. My differentiated, the rate of change of bacteria over time, is 4 minus 32 t to the power of minus 3 over 2. That's 3 marks right there. And the last part says we've got to find the points at which the number of bacteria is increasing. This is where the inequalities come into play. A function is increasing when it is greater than 0. So we set this equation up, the rate of change, to be greater than 0. If I wanted to know when it was decreasing, it would be less than 0. And so we solve this as is. So 4 minus 32 t to the minus 3 over 2 greater than 0. I'm going to bring the minus 32t to the minus 3 over 2 over to the other side, and I'm going to rewrite my indice in non-indice form. So I'm going to change the minus a half means root, and then it's t cubed. And now I'm going to do the ill-fated idea of cross multiplying, but this is where t is greater than 0 is always positive, because you know in inequalities when you multiply or divide by a minus number it changes the direction of the inequality. Well, we know 4 is positive, we know 32 is positive, we don't really know about t, and if t was negative this might change the direction of the inequality, but t was told to be greater than naught, so this is always positive, and when I multiply across it's not going to change the direction of my inequality. So I'll do 4 times square root of t cubed is greater than 32, and then I'll divide across by the 4 to give me the square root of t cubed is greater than 8, which is 32 divided by 4. Once I'm at this point, I'm going to do inverse functions the whole way along. So the inverse function of a square root is to square it. So I'll get t cubed is greater than 64, and the cube root, the inverse function of a cube and something is cube root, the cube root of 64 is 4, so t is greater than 4. So the region of values, the range of values is when t is more than 4 seconds, the function will, the number of bacteria will increase over time. And that is that question done. Okay. Like most of these questions, it's about practice. When I work through the past papers problems that there are coming up, you'll see a couple of other ones that link maybe a bit closer with some of the inequalities that you'll do directly in C1, rather than being part of a differentiating question, and you'll see those solutions work through. But that is finding the rate of change of increasing and decreasing functions. Next time, we're going to use differentiation to find optimal solutions to problems and examine techniques in building algebraic expressions, which tends to be the hardest part of the top parts questions, if you know what I mean. When we're using optimization and differentiation, the building the algebra expressions tends to be the bit that most people struggle with. So I'll look at some of the techniques that come with that. Our objectives were to find the equations of tangents and normals to curves, and find the regions of increasing and decreasing rates of change. Both those have been done. Practice, practice, practice. For more exercise solutions, quizzes and downloads, go to FlipMath and search for differentiation down at the bottom of the page and pop it in the search box. Feedback on all resources should be sent to @FlipMath on Twitter. You can like and subscribe to the video, and if there's any obvious errors or suggestions, please contact me either at FlipMath or in the comments of the video. Thank you for watching, and I'll catch you next time. Bye!